This video is presented to you by Physics for Students. To know more, please visit us at physicsforstudents.com.
Okay, so this video is about refraction of light, and I would first like to express my thanks to Mr. Devinder, who actually requested me to make this video. So I'm really thankful to Devinder, who is already doing a great job by teaching students. So this is my video on refraction of light, and thankful to Mr. Devinder to giving this opportunity to make this video. So before we proceed into propagation, the theory of light, first of all, let us understand what is the meaning of the word refraction. Now, as you have been watching in most of my videos, what I try to do is that I try to go back to the basic, that is the Latin origin of the word. Because if you see most of the words which we learn in biology or mathematics or even in physics or science, they have their origin in either Latin or Greek. Right, so it is better that we can understand the meaning of the word, and then we can understand the underlying meaning. So this word refraction is coming from the refractionum, which actually means breaking up, or the refringer, which means to breaking up, and it dates back to around about 1570-75, and it carries its origin from Latin. So as most of the words which we deal, as I told you, leads with Latin and Greek. So refractionum or refringer actually means to break up. Further, we can divide this word refraction. If we trace back to the origin, it is re plus franger. So re actually means going back to the original place, right? As in English we have words like rewind and replace and revisit. So re actually means going to the origin or going to the original place and going back, etc. And franger is basically means to break. So if you want to make up this word refraction, it means a kind of a breaking again, or going back to break or something like that. And that is why in English these words, for example, fraction, fragile, fractal, okay, all these have their origin in Latin. So franger means break. Also you need to know that there is a word called b-h-r-e-g. B-h-r-e-g, break. It actually is an old word which also means to break. So fraction and fragile, so you understand fraction is breaking up a whole number, fragile is something which breaks down, fractal. So all these have their origin in the Latin word franger, or to break, something like that. So this is basically just a note on to trace back to the origin of the word refraction. Now if we go to the definition part of refraction, you might see here 2 or 3 more definitions, but it is good to read all of them so that we can have a solid understanding of the concept. So the first one, it shows deflection from a straight path undergone by a light ray or energy wave which is passing obliquely. This is important. It should pass obliquely. We will come to know why it is so. You can also call it bending of light when it passes from one medium to another. It is change in the direction of light and change in direction of a wave passing from one medium to another, or from gradual change in the medium from one to another. So 1, 2, 3, 4, all this definition actually explains one central concept, that refraction actually means deflection of light when it moves from one point or one medium to another. Central idea is it is bending or it is deflection, and the change of the direction is what is called refraction. So all this definition gives this central point, deflection of light passing from one medium and moving to another. Well, if you see right on the screen, there are two division. One is the purple and is the lower is a very light kind of a blue, and we have got two medium, just as we read that the refraction is basically deflection of the light ray from one medium to another. So on the top you see it is air, and at the bottom you see water. and I draw what is called a perpendicular, just a normal, because in most of the geometrical or physics drawing we draw perpendiculars, so that for Cartesian coordinates it becomes easy for us to get the angle and do all kinds of calculations. So here is a light which is falling, right? It falls here and it should have gone in this path, which is the dotted one, right? The light coming in, falling from air and moving into water, it should have taken the path, but it is taking this kind of a path. Why, when, we are not coming right now, we will explain further in the video. So what it forms is that this one which you see, the first line, is called the incident ray. So you can understand incidence actually in English means some kind of an event. So the first light which is falling is called an incident ray. This angle, the green one which forms, is called an incident angle, which is measured as θ1. You will later find it is called I for incidence. The next one is the refracted ray. So as we have learnt in the definition that refracted ray means the light which is deflected. So you see the light is deflected, so it is called refracted ray. And what we get more is this one, the green one. This is called a refracted angle. So the incident ray falling creates an incident angle. The refracted ray which is deflecting creates a refracted angle, which you can call R, and you can also call incident ray as I. Doesn't mind. So notations are simple. And we get something in this dark red. It is called angle of deviation. So from the perpendicular or the normal, how much the light is deviated, we call it an angle of deviation. So these are the few things which I just wanted to tell you, that when light is deflected from one medium to another, we draw normal so that we can calculate the angles. The first line falling is an incident ray. The deflected one is the refracted ray. The incident ray forms an incident angle. The refracted ray forms a refracted angle, and we get an angle of deviation. Right. Now if I take the picture, the same one, the incident, perpendicular, normal, and just I minimize on the left hand side of the screen, we can define now what are those things which we have just seen. So incident ray is a ray of light falling on the surface. Separating two mediums is the incident ray. So this one is the separation medium between the air and water. We get refracted ray, which is a ray of light which is deflected, traveling in another medium with change in direction, is the refracted ray. We also get an angle of incidence, the angle which the incident ray makes when the normal is called the angle of incidence, which is the angle of incidence. And we get an angle of refraction, okay, which I have not shown in here. We'll come to the later part. The angle which the refracted ray makes with the normal is called an angle of refraction. So incident ray, the first one, refracted ray, the deviated one, the angle of incidence which is formed with the incident ray, and angle of refraction, which the angle with the refracted ray. Right. Now we come to something which is called a rectilinear propagation of light. Now linear, as you understand, means straight. Okay, linear motion, linear algebra, linear momentum, linear force, all these means straight. Now what I wanted to tell you is that light, just like human being, well this is just an analogy, light like human being has a unique tendency of moving straight. If you see, for example, if I am moving from my room to my kitchen or from room to my washroom, I would generally go straight if I do not face any kind of a, what I would say, any kind of a deflection. Say for example, there is a water on the floor or somebody is sitting, so I would take a turn. Otherwise I will flow straight. So the rectilinear propagation of light, it is something like you see a light bulb, and on the right hand see the observer of the light, and when I shine the bulb, the light ray flows straight, right? It flows straight. So what we define is that we call it a propensity of light to travel along a straight line, right? Mind it, the propensity of light to travel along a straight line. Propensity means it describes the tendency of the light or electromagnetic waves to travel in a straight line, right? So propensity means it has got a tendency. which is a natural tendency. As I told you, when I am moving from my room to my washroom or to my kitchen, I have got a tendency to move forward, straight, rectilinear, unless there is an obstruction. So I can tell that light does not deviate when it is traveling in the same homogeneous medium, right? So same homogeneous means water to water, it is straight, glass to glass, it is straight, and air to air, it is straight, right? So it is a tendency of the light generally to move straight. Again, I would like to stress upon this word propensity or tendency, because once we go further in this video, we will see that this propensity changes. As I told you, when I am moving from my room to my washroom, until and unless there is a water, there's a blockage, or my children are playing, I won't be moving in a different line. So my tendency, a propensity, is to travel straight, and so does light, and in the homogeneous medium it moves straight. Now I was just going through some books. There might be a question which you might find, that rectilinear propagation of light is due to velocity, wavelength, high frequency. Which one? So it is due to high frequency. So rectilinear propagation of light is the propensity, tendency to move forward, and it is because of high frequency. Okay, so we can see some examples. For example, this is a ray of light which will go straight. These are beams of light which goes again straight. There's a spherical movement which is generally done in this way. So these are the beams of light coming from source, right? And these are directional light, parallel light rays. So can you see something very unique in this 1, 2, 3, 4, 5 pictures? That all of this actually leads to rectilinear movement of light. Light has the propensity or tendency to move straight. So ray of light or beam of light or spherical, or it is being emitted from the center, or it is moving parallel, all of this have got a general tendency to move straight. So now I have just given an illustration that if this is the candle which is burning and that is the globe or an object, so if I shine the light, it will go straight and forms a shadow right on the opposite side. So this is another example that why shadows are formed exactly opposite to the object, which is parallel or coming straight from the source. So the source is the candle. As you see, the light shadow is not formed here, this yellow part, nor it is formed here, right? It is formed exactly on the opposite side of the object, which actually shows that light has the propensity to travel straight, or the rectilinear movement of light. Okay, so now we need to know a few terms before we move into refraction. What is a medium of propagation? Now when we talk of the literary term propagation, it actually means to spread. Okay, propagation means to spread. So if I can draw a picture, it shows something like this. So any material which is used for propagation of signals. So I can say the propagation of medium, a material that enables transfer of energy. So a medium is something which enables the transfer of energy. Propagation can be many things. Propagation of ideas, propagation of organisms, propagation of waves, right? So sound is a sequence, for example, of waves of pressure which propagates through air and water. Waves in water propagates only in water. Electromagnetic waves and gravity does not require a medium to propagate, so it generally propagates. So I can tell this picture, which you can see as the light is moving. This is a nice animation of electromagnetic movement. So it requires a medium, right? A medium is the material which enables the transfer of energy. It can be sound energy, light energy, electromagnetic energy, anything. As you see, this is a speaker which will emit the sound, and this is also another thing which emits. So you see this animation on the right hand side, that it is emitting sound. So the molecules, so the molecules are spreading. So this is the medium air, and the propagation is spreading it out. And also this is something which I have taken from Einstein's online website. This is a kind of a animation which shows gravity or gravitational wave which is propagating, right? So propagation, now we understand it is a means spread of ideas, organisms, energy, anything. And the medium is something which is required in order to spread. So the medium actually enables the transfer of energy, right? Now, for example, I take a very simple example. So now this is a person who wants to move to this gate or to the door, right? So this is the line which is showing that he will be moving towards this. And I find lot of people around there, right? So, you know, somebody is obstructing, somebody playing, somebody doing a mobile, boys, girls, women, men, etc. So what will happen if this person wants to move to this door, the exit part, it will take a lot of time for him to move. Why? Because he has to go through many people, because he has to fight, he has to stumble, there will be struggle, etc. Right? So this person will take more time to reach the door. Now let us take another example. The same person is moving in this direction and he wants to reach to this door, and there are just 1, 2, 3, 4 people, right? Instead of a huge crowd, this person has to reach to this gate and he has to stumble or fight, or you have to struggle through less number of people. So what will happen? This person will take less time to reach the door. Now why I am telling you? Because light behaves in the same manner. So as I told you that human beings and lights have a general propensity or tendency to move. So this person fighting, stumbling, going left and right will take more time because there are more obstructions around there. This person will take less time because there are less obstruction. So he will reach more time to reach the door, and he will easily move towards the door. Now this is why I told you that we need to now learn the term what is a rarer and what is a denser medium, right? Now in case of optics, which we typically called, optically denser medium is the medium in which the speed of light is less. That means it is very dense. That means there are many people, you can imagine, standing in front of you, and you have to go left and right and push and elbow and fight with many people to reach to the ultimate destination. So you are moving through a denser medium, which is water and glass. That means it takes more time. Now, if I talk of the, for the rarer medium, the medium in which the speed of light is more, obviously air. That means you can imagine few people are standing in front of you and you can just quickly go to the destination, that is the road. So I can tell that optically denser medium are when we are comparing two medium. This is important. This is important, that until and unless we are comparing two medium. So you see there we have used comparative adjectives, rarer and denser. We haven't told rare or dense or rarest or densest. No superlative degrees, right? Rarer and denser. So optically denser medium are when we are comparing two mediums, right? Two medium, when we are comparing, we can tell this is rarer than this is denser than this. So rarer means less obstruction, less obstruction, light moves straight. Denser means more obstruction, light moves a little bit slow. Okay, so we take an analogy and we take the same kind of a thing. There we have two medium, air, which is a rare medium, water, which is a denser medium, and we got a oblique line, straight line. This is the ray of light, which we call incident ray falling on this. Again we draw perpendicular. As I told you, it is easy to calculate everything. And then the light should have reflected on this dotted path, but it goes right here, and this is the refracted ray. So the light should have moved there, which we have seen it goes in there, right? It forms an angle of incidence as usual as θ1, and it forms a refracted angle, which is the θ2, and it forms an angle of deviation, which is not much of importance. Now what is important is that the light ray bends towards the normal when it moves from rarer to denser. So this is point number 1, which you should remember. Whenever the light ray, it is falling obviously obliquely, that is not direct to the perpendicular. When it is falling obliquely, that means the incident rays should go on over there. It moves towards the normal, towards the perpendicular. It is moving from rarer to denser. Why? Because I have to struggle and elbow and push around lot of people. so that my angle would be deviated. It will be deviated towards the normal. All right. So this is a classic example. So you can do it at your home. You can take a glass of water, put a pencil or a pen, and you see that the pen, yellow one, which should have gone in this way, looks this. Why? Because the light is refracted towards the normal, and if you draw perpendicular, you will then measure it out. So it has shown the refraction. That means it is not this way, it is on the other way. Now if I take the same thing and I change it from water, now I am moving to air, right? It is just the opposite. So the light ray passes in obliquely from water. I draw incident ray. I draw perpendicular as usual for calculations. And the light should have gone in this way. Now the light moves in this pattern, right? It moves in this way. So we get the refracted ray, which is that one. And then I get an angle of incidence, theta 1. I get an angle of refraction, theta 2. And now I see that the light ray bends away from the normal. From the normal, it moves away. Why? Because from denser to rarer. That means from more people, I am moving to less people. You can imagine it in this way. So light bends away from the normal. Now you see there is another thing which is particularly observable, that the refracted ray is more, right, when the light bends away from the normal. And if you go back to the previous one, let me just go back to my previous one. So here the refracted ray is less. The refracted ray is less. Where here if I go here and I show you, this is more, right? So the refracted ray is more. So from denser to rarer, the light bends away from the normal, and from rarer to denser, the light ray moves towards the normal. Now let us take another typical case. Now water, it is moving from water to air, and the light is falling directly straight, right? It is not an oblique ray, it is falling straight. And now I draw, this is the incident ray, I draw normal, right, straight, right? And what happens is that now you see this is something which a very renowned professor, Professor H.C. Verma, actually explained in one of his videos. I just taking that example. Now when the light is falling directly to the normal, right, straight, not oblique, straight, the light would have gone in this way, light would have gone in this way. If it is a three-dimensional case, maybe other faces, this, that, etc. So light is now confused. Okay, so the light ray doesn't know where to go. This way, that way, this way, that way, where to go. Now you tell me that where the light will go. The propensity of the light, or the tendency of the light, is to move straight, as we have seen in the propagation of light. So it moves straight. It moves absolutely straight, right? Now the question is that this is the refracted ray. Now you see the theta 1, that is the incident angle, and the refracted angle, which should have formed, they are parallel to each other, right? That is why it is all 0 and light ray doesn't bend. So this is a typical observation. When the angle of incidence and the angle of refraction are both 0, that means they are parallel to each other, light ray doesn't bend. Light is confused, it doesn't know where to go, it goes straight, as usual, like human being, right? Now the question is that, can it be called a refraction? Yes, it can be called refraction. It can be called refraction because bending is because of refraction. Refraction itself is not bending, okay? Bending is due to refraction. Refraction is not bending. Since we are changing the medium, and so from water to air, there is a refraction. So bending is due to refraction. Refraction is just the medium change, and we call it refraction. Now, if you see in this way, so it is called refraction. Now what happens is that the sin I and sin R is 0, which we will learn in the Snell's law. Now if I put sin I over sin R, it is 0 equals by 0, and the value is indeterminate. Okay, the value is indeterminate and it is not infinity. This is something very important. Most of the students, you will see, they make a confusion that 0 upon 0 is infinity. No, it is indeterminate. Indeterminate means it can have any value. it can have just any value. That is important. So indeterminate is not infinity. Indeterminate means it can have any value. So this is something very nice. Why the light ray doesn't bend? Because it is confused. It really doesn't know where to go. If you learn earlier physics, there is something called symmetry of nature, which I don't want to go, also shows that light goes straight. And we will see at the end of the video something which we called bend it like Beckham, right? I call it bend it like Beckham. It is a surprise which we will show you. Okay, so till now what we can summarize: incident ray falling oblique from rarer to denser, air to water, bent towards normal. From water to from denser to rarer, it bends away from the normal, right? Incident ray falling normal and not changing, there is no bending. So one is bending towards the normal, one is bending away from the normal, and there is no bending when incident ray falls perpendicular to the normal, right? Okay, so now we come to another term in optics which is called optical density. This is what we need to know before we move into refraction. So optical density is not the mass density, right? Remember, it is not that mass calculation density. It is the process of transmission or other electromagnetic radiations by matter. So if I want to make it simple, I can tell it is the ability to absorb the power of the given light, which you can call it as a radiant power. Okay, so it's optical density. First of all, it is not the mass density, it is the ability to absorb the power of the given light, and it is called absorbance of material. Now this sluggish tendency, why I wanted to tell you, let me explain. Sluggish tendency of the atoms of a material, it means it is going a little bit slow. As usual, nature is slow, just like human beings. We are very slow. We get up late in the morning. We don't want to go for a morning jog or something. So sluggish tendency of the atoms of a material generally to maintain the absorbed energy of an electromagnetic wave in the form of vibrating electrons before re-emitting it as a new electromagnetic disturbance. So the more optically dense it is, the slower it will move. So here is something. So what I am trying to tell is that this sluggish tendency, it has a tendency to maintain the absorbed energy of the electromagnetic wave which is going into the medium, right, in the form of vibrating electrons, and then it re-emits it as a new electromagnetic disturbance. So let us see the further definition. In rarer medium, speed of light is fast. Why? Because as I told you, the electromagnetic vibration, when it fights with those people, as you can make an analogy that they're fighting, moving, elbow, this, that. So the electromagnetic waves which interacts with the electrons or protons or the waves with that particular medium, when it interacts, it becomes slow. Obviously, if you interact with more people, it will take more time to reach, and in denser medium, speed of light is slow. Now, this is important. Refractive index is a measure which medium is denser and one is rarer. So refractive index measures which medium is denser and which medium is rarer. Now you might have a question. So you understood one thing, this sluggish tendency, it is slow, it will interact more with a denser medium, the electrons and protons and the waves will interact, so it will become slow, right? And it doesn't interact, it becomes faster. So the ability to absorb the power of the given light, that is called the optical density and called the absorbance of material. Now you might now have a question. Okay, let us first define the definition of a refractive index. Refractive index determines how much the path of light is bent or refracted when entering a material, right? Now here I would like to tell you that we know that light is an electromagnetic wave, right? Electromagnetic wave with both electric and magnetic field alternating. Now in vacuum, it freely propagates, it freely moves. Falling on a medium, it interacts with the electrical and magnetic properties of the medium. Interacting with those properties slows down, and those properties define refractive index. So the refractive index of a material is a number that describes how fast light travels through the material, also known as refraction index or index of refraction. It is a measure, that means it's a number, right? It is a dimensionless number of how much speed of light changes when it enters the medium from air. Now you might find there is a what is the relation? I told you about optical density, that is, which is called the absorbance of material. Now I am talking of refractive index. What is the relation? The relation is this. So higher the refractive index, that means more optically dense it will be. Obviously in water, if you're fighting with more molecules, fighting with more people, that means the optical density is more. That means interaction is more. That means refractive index will be more, right? This is the relation between refractive index. So here is something very, very important. Optical density is a property. Refractive index is a measure of it. Now let me give you another example so that you can really visualize things well. Now say for example, you are standing at the seashore and you see a person drowning. Now this is an example which Richard Feynman proposed in his Feynman lectures on physics. I'm not going into the mathematical part. I just wanted to tell you that, say for example, you're standing on a shore and you see a person drowning. What will you do? Initially from the shore you will move, you will run. Why? Because you know at this point running will cover more distance and you can move much faster, closer to the person to save him or her rather than swimming. Right? So you will run fast and then jump into the sea, swim and save that person. So that is why we call light follows the minimum path. As I told you, the propensity to follow in the straight line, so that is called the minimum path. Right? So refractive index also does so. So it will follow the minimum path. Might not be the path is always straight. You have to go this way or that way. You have to take a turn around the road. Anything, doesn't matter, but it will follow the least minimum path, right? Now this is refractive index and optical density and speed of light. So refractive index is more, speed of light is obviously less. That means more optically dense, less would be the speed of light. Now this is given by this formula, n, which is the refractive index, followed by the velocity of light by the v. So let us see what it is. This is the refracting index of the medium. C is the velocity of light, the famous C, and v is the velocity of light in the medium. In the medium means the medium in which it is entering, right? So let us see a quick example on that. So it can also be written as this, inversely proportional, right? We will come to this part. So if the speed of light is 1.5 multiplied by 10 to the power 8 meters per second, what would be the refractive index? Let us see if we can calculate. So we just know n equal to c by v. We put the value of c, which is we already know as 3 into 10 to the power 8, and we put the refractive index. We cancel them out and simple, we get n equals to 2. And when it is called n equals to 2, that means there is a refractive index of 2. That means light is moving into a medium which has got a refractive index of 2. What is that material? It is round about 2 to 2.5. It is called boron nitride. So once we get the refractive index 2, 3, 4, 5, 1, 0, we can now understand that which medium the light is entering, which medium the light is propagating. Now you understand optical density and refractive index. So denser the medium, the higher the refractive index. So optical density gives the density of that part and refractive index measures it. So we take another example. Given the speed of light is this and the velocity of light in glass is this. So what is the refractive index? Simple. So this is the solution. So we write it in this way: C subscript vacuum, V glass, right? And we do this, right? And we get n equals to 1.5. So this one, we cancel out the 10 to the power 8 for both. This is called the refractive index of glass. This is a measure which gives the how much. Now when I get n equals to 1.5 by doing this calculation, what do I get, right? So what do I get from here? What we get is this. This shows how much glass is denser than air. It is 1.5 times denser than air. I told you that when we are talking of denser and rarer medium, it is all but how much one medium is denser or rarer. So there is a comparison. So one is that how much glass is denser than air? It is 1.5 times. Next is that how much the speed of light will slow down? It will slow down 1.5 times. So this is a good analogy that refractive index actually gives two measure how much one medium is denser or rarer than other and how much the speed of light will slow down. So we can do this one. The refractive index is given with respect to w.r.t as 2 mu1. So how we write it? So now you see refractive index of glass with respect to air. Glass is on the right hand side, air is on the left hand side. This is a usual convention. Refractive index of glass with respect to air, glass on the right hand side, water on the left hand side. This is one way. There are numerous other ways you can write. So can we solve this? The refractive index of water with respect to air is this, glass is this. Find the refractive index of glass with respect to water. So we will just show you how simple it is. So what we do, refractive index of water, we know this. Refractive index of glass we know is this. And refractive index is mu g by mu w. Mu is the measure. You call the refractive index n or mu. It is just the measure, right? So we get a mu g and a mu w. So this is just a very simple, this is not much of a physics or mathematics into it, just to show you that how we calculate. Okay, so this is another example. Refractive index of glass with respect to water is this, glass with respect to air is this. Find the refractive index of this. So what we do, we write it in this way, and then we write the refractive index of glass in this way, right? And then what we do is that refractive index of with respect to air is this. So you can just take a note if you really want to look into it. Otherwise I think it's pretty simple, you can just solve it. So what we will do from the next slide onwards, we will discard those red ones because it comes very confused, mu wg this side and that side. So I will discard those things and I will take it in this way. So it is 3 by 2, 9 by 8. So we write it in this way, 3 by 2 and 9 by 8. So from here, both mu g we get it, we move to here, right? And we compute this, right? And we get 4 by 3, which leads to this. So the refractive index of water with respect to air is this one, right? So this gives a kind of a calculation of one refractive index with respect to other, how you can do. Now we come to the middle portion of the video, which is Snell's law, right? And I just wanted to tell you that this is important to every level of physics for students and to everybody. So Wilbord Snell van Rooyen, he was basically a Dutch astronomer and mathematician, and the lunar crater, if you are more interested, you can look, lunar crater Snellius is named after him, and he did an important work in optics. He died at a very young age, you know, at 46, and most of his works is in Latin, as you know. Even Isaac Newton's Magnum Opus Principia Mathematica, it is in Latin. So during those days most of the works were in Latin, and that is why I told you we need to learn the origin of the word refraction, because Latin gives that kind of a tendency, right? So this is one. So Wilbord Snell van Rooyen is basically the Dutch astronomer. He founded what is called a Snell's law, and if you have ever visited his house at Leiden, if you're standing on the opposite side, you can see the Snell's law is engraved on his building. Yeah, it is engraved on the building, just like for example Stephen Hawking's tomb is engraved with his famous Hawking radiation formula. But prior to van Rooyen Snell, so yeah, so it defines the relation between angle of incidence and an angle of refraction. Prior to that, there was even before him there was a Persian mathematician called Ibn Sal. Okay, there's a Persian mathematician, the first Muslim scholar who worked on the works of Ptolemy, the Greek mathematician, on optics. And he is the history says that Ibn Sal was the discoverer of Snell's law, and works with a number of things like parabolic mirrors, ellipsoidal mirrors, biconvex lenses, a lot of works in optics by Ibn Sal. Okay, so that is a nice kind of a history to let you know. Now this is actually the Snell's law, right? So it actually shows that the ratio of the signs of the angles of incidence, the angle of incidence is n1, which you can call as I, and n2, which is refractive, you can call it R. So ratio of the sines of the angles of incidence and refraction is equivalent to the ratio of phase velocities in two media, or equivalent to the reciprocal of the ratio of the indices of fraction. Okay, I will come to this part later. So the ratio, as you see, n1 by n2 is constant for any given wavelength. We will see examples of light. The ratio of the two sines is also constant for any angle. So hence we can say that it is a relationship, right? This is Snell's law, is a relationship between the path taken by the light in crossing the boundary. So the incidence, you imagine it falls from the light in crossing the boundary or surface of separation between two contacting surfaces of the refractive index. Now this is more or less, so whatever I have told this equation, I will just show you in simple examples. So just understand that this is basically speaks of the ratio of the sines of angle. It is a constant for any given wavelength, and the ratio of the sines is also constant for any given angle. So this we will see how it works out. Now remember one thing, that Snell's law actually works in isotropic medium, not on anisotropic medium. By isotropic medium, I mean to say that isotropic medium is a medium in which all the properties are uniform, right? All of them are more or less same. For example, you can call it, say for example, glass and water. More or less the chemical, I can say that they have the same consistent chemical bonding. They have the consistent same chemical bonding, and they have the same refractive index. So iso means similar, isotropic, isomorphism, isotropy. So iso means same. So any material which has got the same chemical or constituent or chemical bonding, it is isotropic. Anisotropics are wood and crystals and cube crystals, so on. So we are not going to take into anisotropic medium. So isotropic medium is where Snell's law actually works. In anisotropic medium, what happens? We are not going to deal with that in this particular video. So we get this ratio V1 by sine theta 1 equal to V2 by sine theta 2. Now what does Snell's law states? So it states that the ratio of the sines of the angle of incidence and refraction is equivalent to the ratio of the phase velocities in two media, or equivalent to the reciprocal of the ratio of the indices of refraction, which I have seen earlier. Now by phase velocity, just try to understand that phase velocity of a wave is the rate at which the wave propagates in any medium, right? It is rate at which the phase of waves propagate in space. We can also see that is the definition of phase velocity. So the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant. So sin I by sin r equal to a constant, which is mu, which is the refractive index. So here you see this is the sin I, which is angle of incidence, sin r, angle of refraction. And it is obviously true in isotropic medium, which I have explained earlier. Now let us see a few examples which will make things clear. So from vacuum, there's a straight, there's an oblique line which is moving from incident to here. So the refracted ray, we draw a normal, we get an incident angle, we get a refracted angle, and this angle is at 30 degree, right? So we use this formula, V1, this one, and how do we get it? So we put C is equal to sine 30, which is the incident of angle of incidence, that is sine theta 1, and V glass, that is sine theta 2. Now you see this one is actually the C, the famous speed of light, which we already know. Sine 30 is round about half, and this one is the velocity of light in vacuum, in glass. So we have given that, and from here you can easily calculate sine theta 2, right? That is why I have circled in red. I don't want to calculate. So this actually shows that we can calculate the refractive index sine theta 2 using Snell's law, right? So now you can understand the use. So we can write Snell's law also as this one, right? And this one, this can be written as this. So V equals to C by N, which I can do a little bit of algebra, and I get this, right? And I can get this one also. So I can put C N1 sine theta, C N2 sine theta from this, right? Let me show it again to you. So this follows from this, and this follows from this, right? So I substitute V1 instead of C by N. So instead of writing C by N, because we have two, we write it C by N1 and C by N2. So I substitute V over there. and then I multiply both sides by n1 and this side by n2. What do we get? We get this, and from there we get this. So we can, again, I've just skipped one step. We can multiply both sides by c and get it cancelled out, and we get this. So this is another way of writing Snell's law, where we substitute the velocity, cancel things out, and get this, right? So now we have two formats. One is this, which is for velocity. One is this, which is for refractive index. Both of them will be useful, right? Depends on what problem that we encountering. So another way of writing refractive index of glass with respect to this. Okay, now this is just to show you another way of writing. Suppose that velocity v1 and v2, it is moving from mu1 to mu2. As mu1 increases, that means refractive index is more. Obviously the velocity of light decreases, as you know. So it is moving into a denser medium, the refractive index is more, and the velocity of speed of light slows down. That means mu is inversely proportional to velocity. Obviously, if mu increases and v falls, then I can write it in this way. So I can write it in this way. Mu2 with respect to mu1 is v1 by v2, and this is written in opposite direction. In front of u2 we write v1, in front of u1 we write v2, because it is inversely proportional, right? Now let us see a small example with this. We're coming to the almost to the end of the video, where I've got a small surprise for you. So if it's getting glass and air with this, and I write it in this way, and I put those values, cancel things out, we get this. I'm so sorry. Yeah. So this is just to show that instead of writing the other way, we can also write it in an inverse way, and we can get the same value, right? Okay. So Snell's law also tells about one thing, that if I am moving from this direction, the incident ray changes to this in the second case, changes to this, which becomes more in the third case, changes to even more, it becomes lesser in the fourth case. What we get is that sin I by sin r is a constant, right? And we can solve problems. So we have seen that this is a constant, and we have seen that in the what I would call the definition also. So if I get something r equals to 14 degree, that is the angle of refraction, and the medium is 1.2. So I can put this formula, sin I upon sin 14, which is the refractive index, equals to the, this is the, sin 14, that is the degree in which is refracted, and 1.2 as a refractive index. We can do this one, sin I equals to this and to this. So just I put the value, approximate value of sin 14, and I get this. Then I calculate sin I from here, and I get the, do the sine inverse, and I get this one. So that is why I've written approximate. So what does it show? That once the values or the refracted incidence ray is changed, yet it remains constant, and with this we can get the sin I, that means the angle of incidence from the Snell's law. Now this is just a problem for you. Let me know if you can solve this. This is pretty simple, problem. If the angle of incidence is 25 and refraction is 32, find the refractive index. Do let me know in the comment box, right? So just a few examples before we end this video using Snell's law. So you get this one, you can read it out. Into an optical fiber, 1.44, light bends, angle of incidence is 22 degree. What is the angle of refraction? So I write that since the light is traveling from rarer to denser, lower to higher, it will bend towards the normal. So I consider air as medium 1, fiber as medium 2. I consider as 1.00. That is, now this is air as medium 1, the refractive index, it is in vacuum. Okay, air always doesn't mean vacuum. So I just take an ideal condition, and I get I equals to 22 degree. Then it takes the Snell's law. Snell's law turns into, so N1 is 1. Sine theta is sine 22, which is given on the top, right? That is the, and then I put on 1.44, and then I want to calculate the sine theta 2, which is the angle of refraction. So I just put this in the opposite side, and I get sine theta as this, and from there I calculate this one, and I again take the inverse, and I get this theta 2. So this is more of 15.61 degree. So this is, what is the angle of refraction? This is the answer. Now if I want to show this, this is the line, which is how to draw the diagram. Roughly I have sketched, it is not, maybe not accurate. Another problem, light traveling in optical fiber 1.44 reaches the end, angle of incidence is 30 degree. And there is a part B is that how would you answer if they will be different from 50 degree? Let's see that. So we solve this from fiber 1, material 1 to 2. So I take 1.44 which is given and N2 as 1. So it moves in a, from 1.44 it is 1. Yeah, I equals to 30 degree. Snell's law, again we take it. We've put the value 1 sine 30 degree. Again we are trying to find the refractive index sine theta 2. We get this value. So I've just substituted the approximate value of sine 30. We get from here and we get the sine inverse and we get theta 2 as 46 degree. Right? So this is the answer for the angle of incidence at the end of the file. What is the angle of refraction? Theta 2 or I is 46. So this time the angle of refraction is larger. Why? Because the light is bending away from the normal. Now if I replace it by 50 degrees, right, what will happen? See this. This remains the same. I put the value of sine 50 degree and it leads to nowhere. Right. Sine 50 is 1. I cannot calculate this one. This is not possible. So I cannot take a sine inverse of theta 2. Right. So that is why this is cannot be computed. Hence this is called a total reflection, which is not the part of the video. But this is why the total reflection happens, or this is an ideal problem of total reflection. So just another example, a beam of flashlight traveling in air which is 38 degrees to the normal. So you see 38 degrees from it is traveling where at an angle of this is it, the index of refraction is in the glass is 1.56. So from air I'm moving to glass, right? So again I put those values and take this and I take this and I take this and further I go into this. So I put the value of sine 38 degrees, sine theta 2, everything is fine. Yeah, I take a sine inverse and this is the refractive angle is 23.25 degrees. So I'm just showing you similar examples because in our school days we used to do similar kind of examples to get a grasp of the concept, right? Boy is in a pool. That means the water, the light is going from water to air, right? And hit it at 35 degree at an angle. What is the angle of flashlight beam on the pool? So I have just drawn it 35 degree from the water towards the air. N is 1.33. So now you see here this one. So N1 equals to 1.33, N2 is equal to 1.00. I have just renamed that so that it is easy for you to understand. Ni, angle of incidence, Nr, angle of refraction. So we do it in the same way, nothing more. We just substitute these values. By calculate this, sine 35 is approximately this. I take an inverse and it is not equal. Anyway, it would be more or less this kind of a refractive angle. So these are similar examples just to show you how Snell's law works and how refraction works and how you can calculate the refractive angle when light moves from different medium. Now this is something important. Fermat's principle of least time. You know, I think you all know who was Pierre de Fermat, the famous Fermat's last theorem, which was solved years back by Professor Andrew Wiles. So light travels this refraction. Now you might ask me why at all the light is bending. We understand this, that, mathematics and index and denser molecules colliding, by why light bends. I mean to say the grassroots level. This is the reason which I will understand now at the last of my video. Light travels between 2 points along the path that requires the least time. The sluggish, the propensity of light to travel, which will be the least path as compared to other nearby paths. That means if there are other nearby paths A, B, C, D where the light can travel, it won't travel. It will travel between 2 points along the path that requires the least time. So the angle of refraction, or the Snell's law, which I might explain in another video if you want me, comes from Fermat's principle of least time. It is derived mathematically from Fermat's principle of least time. Okay, now the last part of the video. Why does light fall perpendicular on an interface doesn't bend? This is again a nice video by respected Professor H.C. Verma, which I would like to explain it in this way. Now let us say it is a cube. Okay, it is not a flat surface, it has got a three-dimension surface. We got a perpendicular and light is falling directly, normal, right? So it might go here, it might go on the other surface, it might go this, it might even go this, or it might even go, sorry, these are the ways, right? So light really doesn't know, as I told you, where to go. On a three-dimension surface, there are infinite amount of possibilities to go. Instead of that, it follows the Fermat's principle of least time and it goes straight like this, right? It goes straight like this. Now, I would like to explain you mathematically why it is so. I understand Fermat's principle, I understand symmetry of nature, I understand propensity of light to propagate in a straight line. What is actually the mathematical reason? So we take the Snell's law again. Now we take V2 sine I equals to V1 sine R. Now in case of an I equals to 0, because incident ray is normal, obviously the angle of both refraction, this is 0. Now I can calculate V2, so this becomes what if I substitute sine I 0, so V2 0 equals to V1 into sine R, right? So I multiplied, this becomes 0, this is multiplication, mind it, V2 multiplied by 0 0 equals to V1 sine R. Now V1 is obviously not the same as V2, right? So what is sine R? So sine R here is 0 because it is normal. So what is V1? What is R? I mean to say R. I'm so sorry. What is the value of R? R is 0. R is 0 means that there will be no bending. So you see, when incident ray is falling normal to the surface, following the Fermat's principle, obviously it will go straight because it is unable to decide. Now you might say, am I speaking psychology? No, it is mathematics. It is the propensity to go straight. It is, I'm just using the term to decide. Okay. So light, how can it decide? Anyway, and using the Snell's law also, when the incidence ray is 0, when the left side becomes 0, what will be the value of R? R will also become 0, and that is why it has got no bending. Right? So that is all. So I have just summarized everything. Refraction, we have learned the definition. What is refracted ray, angle of incidence, angle of refraction, propagation of light, rarer and denser medium, what it is, what are the laws of refraction, optical density, we have learned the two formats of Snell's law, example of using Snell's law, why light doesn't bend when it is falling normal. So that is the last one. So that's it. I think that is quite an exhaustive understanding of few things. I haven't covered the reflection part, which maybe I can cover it in the another part depending upon your comments and your feedback. So just let me know how do you like the basic idea of refraction of light. Okay, and please feel free to comment on the comment section. Please like, subscribe and click on the bell icon so that you get all the notifications from Physics for Students. Thank you very much for watching the video, and stay happy, stay safe, and have a nice weekend ahead.